All right, so we are talking today about significant digits. Yes. Hmm. Yeah, for right now, I might need to move some things around a little bit because I know he's just too tall. He's not very transparent. So
Is this being recorded?
yes, it is.
Like you can hear us?
Yes, I can.
Is this gonna be on YouTube?
That's the goal. I mean, you're not identified on here at all. We might be able to hear your voice on it, but what you can hear is me and see the explanations that I'm writing out for you, so that if you're out, you can go back and look at it. Okay. All right. So what we're going to be talking about today is something called significant digits. At least we're going to begin that process. We're not going to be able to finish today, probably. We're going to begin talking about significant digits today. All right, now the reason we need to know about significant digits is that it is very important in the sciences that we're clear and accurate in what we are communicating. It's really easy to get results in chemistry that are wrong if your measurements and the way you handle those measurements in mathematics is not reasonable. Okay? So there's a way of handling significant digits. We call the significant digits rules. We're going to just begin with addition and subtraction rules. But the first thing I want to do is kind of give you an example of why it's important to know about significant digits. Sometimes you have devices that measure with a different degrees of precision. Now there are two different definitions of precision. There's precision that applies to instrumentation, how precise an instrument is to measure something, and there's precision in terms of repeated measurements. Okay? Yes? Somebody had a hand up over here? Oh, okay. All right. So what I have here is just as in the way of example are a couple of rulers. Okay? So what I'm going to do is measure. What I want to do is to add the lengths of these two lines together. So the first thing I'm going to do is line up this ruler very, very carefully here with this first line and see how long it is. Now, if you're looking very, very carefully, and I could bring the camera down really close, but hopefully you can see this. I've lined this first beginning line up so that the end of this line is right in the center of that mark right there. Okay? And I'm looking over here to this measurement, and what I see is this line is 3 centimeters long. Now, that would have been just fine for most of the classes you've had up to now. But at this point, we want to be as precise as this instrument will allow us to be. And it's actually possible to be more precise than 3 centimeters. And that's where we do something called estimating another digit, estimating a final digit. So what we're going to do is since this is 3 and this is 4, then it's assumed that it's reasonable to assume there are 5 markings that are missing in here. Does that make sense? So we can estimate where this line might come to if there were 5 markings in there. You can always estimate, and I can only estimate to 1 more marking in tenths than exists on an analog device. Okay, this is an analog device. I'll define that for you in a minute. Okay, so let's see. I'm going to assume or estimate that this is not just 3 centimeters, but 3.1 centimeters. Does that make sense to you? Okay, does that seem like a reasonable estimate to you? Okay, so I'm going to put down here 3.1 centimeters. Okay, now I have another ruler over here that measures with more precision. Okay, this measures not just to the centimeters place, but to the millimeters place. Okay, so I'm going to line this one up on this line, and I'm going to try and get the end of this line right in the middle of that marking. Okay, very carefully, and then I'm going to go over here and I'm going to figure out, well, where do I think the end of this line goes to? In fact, this is kind of a clear ruler, so I can actually line this up on top of it and see what's underneath it. Okay, and get maybe even a better representation. Well, if this is 5 and this is 6, each of these markings are tenths. Does that make sense? Oh, this is just great. I hate it when that happens. This happened to me first period, too. There we go. Oh, we're back in. Let's make sure we're capturing here. Yeah, it's still capturing. Good. All right. You can't? How about now? All right, good. All right, so I'm seeing 5.1, 5.2, and that marks somewhere between 5.2 and 5.3. Would everybody agree with that?
Yeah.
Okay. So we can estimate how far it is between 5.2 and 5.3. Anybody want to give me an estimate? Huh? 5.2 and a half? I don't think it quite gets to 2.5. I think it's a little before 2.5. You can't see it?
Well, I can see it.
You don't want to bring it down close?
No,
Bring it close, please. Wait a little bit slower.
Well, I hear 2.1. I see here 2.2. Okay. Both of those are reasonable estimates. 5.21 and 5.22 are both reasonable estimates. Okay? If you wrote down 5.21 and you wrote down 5.22 and you wrote down 5.23, I'd probably accept any one of those estimates. Heck, I might even accept 5.24. That's pretty close. Okay? It's a reasonable estimate. Okay? Now 5.29, nah. Not going to accept 5.26, nope. Okay? It's got to be in a reasonable range. Okay? So let's just for us today, right now, say this is 5.22. Okay? All right. 5.22. Let me raise the camera back up so you can see what I'm doing. And we're going to add these together. Okay. And refocus my little document camera here. All right, 5.22 centimeters. All right. Now remember, our two devices had a different degree of precision. This device was more precise than this one was. It's more precise because it can measure to a finer measurement. Does that make sense? All right. But we have a problem here. If we're going to add these numbers together, our answer is going to be kind of hinky, I guess. Okay? But let's add it together the way it is right now. And this is the process you're going to use in here. So we get 8.32 centimeters. But here's the problem. If I had measured this line with this device, we would have had a digit right here. Does that make sense? You can't put a digit there because in the sciences, if you put a digit there, you're telling everybody that reads that this number or the device that measured it was that precise. And it's not. So if you put a number there, you're lying in the sciences. So we can't put a 0 there, as you've been taught to do in math all these years, right? Okay? But if you want to kind of keep up with a place, you can always put just an arrow or something, okay, just to kind of keep up with it. That's okay. You don't have to put anything. But just to help you keep up with things, an arrow is fine, but a 0 is not. Does that make sense? You understand why? All right. Now, the problem is, suppose this number, if I had measured it with this more precise instrument, suppose this number was a 6. That would make this an 8, wouldn't it? Mm-hmm. We really don't know what this number should be, do we? Basically, that number then is useless to us. Okay? If we're trying to be clear about the precision of these added together measurements, the measurement can only be as precise as the least precise measurement. Does that make sense? Do I need to repeat that? When you add or when you do any math with any numbers, the answer can only be as precise as the least precise measurement. You understand why from this example? Okay. So what we have to do is we have to actually round off here. Anytime you list numbers when you're adding and subtracting, I always recommend at this level that you guys list your numbers vertically, just like you learned to do in 3rd grade. Okay? List your numbers vertically like this in nice, neat columns to keep it up with. Neatness will count here because it makes it easier to keep up with what the numbers or digits you're working with. Whenever you do this, anytime you have an empty slot in a column, the number that results in that column, when you're adding or subtracting, has to be rounded off. That digit is insignificant. Okay? So that's your rule for rounding in addition and subtraction. So we're going to line the digits up vertically, nice and neat. Neatness counts. Digits in the answer. Resulting from empty slots in the column. But only those digits on the right. Okay, so digits in the answer resulting from empty slots in the column, only those digits on the right, are insignificant. That's the word we're going to use, are insignificant. Okay? Insignificant digits must be underlined. So I'm going to go back over here and underline this one insignificant digit there. Okay, now you can have 3 or 4 or 5 insignificant digits. Okay, in this case we only have one. Insignificant digits must be underlined and rounded off with an arrow to show that you rounded. Okay, so here's what that last part means. I'll let you finish writing those notes, then I'll show you what that means. So the rounded answer is going to be 8.3 centimeters. Okay? We need to be clear in the sciences, clear about what we're doing. So I was clear here, showing that this is numbers that are added together. Okay? I need to be clear here about the relationship between this number and this number. We round it off. So this is not an equal sign. These two numbers aren't the same. They're not equal to each other. But what they are is round. This is a rounded answer from this. The way we show that it's rounded is to use an arrow. Okay? I use a little curl or C-shaped arrow. You can use a straight line arrow to the right if you're going to put it over there or whatever, but just you have to have an arrow. The arrow indicates we round it off. Does that make sense to everybody? Just a new little math thing we do in science. And the last thing that I would appreciate you doing is to put a box around the final answer. Okay? Let's see, what was that game show? Who Wants to Be a Millionaire? Final answer, right?